Hi everyone, we'll give it a few minutes for everyone to come in. I know the main session's overrun, so. We'll just give it 60 more seconds. I'm not sure if everyone's migrated over yet. So. Okay, I think we should get going. Okay, so welcome to the TESS KOPS Splinter session at TESS Science Conference. Thanks so much for joining us. I know good morning, good evening, good afternoon. I know it's different times for everyone. So, so I'm Hugh Osborne. I'm the TESS KOPS fellow at MIT and Bern. And first, I thought I'd just tell you a little bit about how we're going to run the session today. So we've got 3 sections. So we'll start off with a couple of short overview talks on the kind of KOPS instrument and the KOPS data and data analysis. And then we'll have 6 science talks, which are kind of the meat of the Splinter session. And then right at the end, there's 5 3-minute lightning talks describing posters, which and these are going to be moderated by Matthew Hooton and Darren Dragomir, as well as myself. And Thomas Wilson, our other organizer, he's going to be monitoring the Slack. And it's quite important. So if you have any questions for any of the people talking in the session, then you won't be able to post it in the chat here on the Zoom webinar. You'll have to post that in the Slack channel, the KOPS Slack channel, which if you're part of the TSC2 conference, you should be able to access that just straight away. So for this first session, the overview session, we don't have any scheduled time for questions, unless we have some spare time at the end, but we'll have to see. But Kate and Pierre will be able to answer questions asynchronously in the chat, as will all of the participants in the Slack channel, sorry, as will all of the participants. So, so if you have any questions for them, just please post in the Slack channel. So we'll get straight away and we'll have our first overview talk from Kate Isaac, who's the ESA KOPS project scientist. And she's going to give us a little 10-minute overview of the KOPS instrument, the mission, and the AO opportunity for proposals. So over to you, Kate.
Thanks, Hugh, and welcome everybody. I'll give a short talk, as Hugh mentioned, to give an overview on KOPS. So unfortunately, Willy Bentz, the PI, and Andrea Fortier, the instrument scientist, were not able to be here, but I'm presenting some slides on their behalf. And then I will go on to mention the opportunity that KOPS provides to the community to share in the excellent photometric precision and sensitivity that we have with the mission. Okay, so KOPS. That's really KAOPS. What is KAOPS? It's a high precision space photometer which is used to observe targets one at a time. So we're looking at the host stars of planets which are known to host exoplanets. So it's a pointed mission. It's an ESA mission, a small mission in ESA's science program, and a collaboration between the Swiss Space Office and ESA. Its goal is to provide high precision photometric measurements in the optical band, so covering the 330 to 1100 nanometer wave band. This is provided without a filter and using a CCD. The targets that we will observe are typically fainter than V-band 12, but we can observe fainter targets, and as I mentioned, targets which are known to host exoplanets. The CCD is fed by a Ritchie-Chrétien telescope with an effective aperture of 30 centimeters, and we have a field of view of 17 by 17 arc minutes. The PSF is a defocused PSF done deliberately in order to maximize the photometric precision that we can achieve, making us insensitive to variations in the pixel, inter-pixel variations, and also to pointing jitter that we have. The spacecraft is a 3-axis stabilized small spacecraft platform, 1.5 by 1.5 by 1.5 meters and around 280 kilograms, including fuel. We're in a low Earth orbit, sun synchronous, in a 700 kilometer altitude orbit going around the Earth. And we're on the Earth on the day-night terminator in order to maximize or minimize our sensitivity to stray light. The mission was selected in November 2012, was adopted in February 2014, and was launched in December 2019. We have a 3.5-year nominal mission lifetime, with the lifetime kicking off from the end of March. So KAOPS is a follow-up mission and looking at one object at a time. And so we have a list of targets in order to be able to observe efficiently with KAOPS. The time on KAOPS is split 80%, 20% between the consortium led by Willy Benz at the University of Bern, and the science team who puts together the program for this part of the observing time. The targets come typically from ground-based RV surveys, and where we will look for the transits of known super-Earths, from the other ground-based transit surveys, for instance NGTS, where we'll be looking to refine the transit depths and the sizes of known Neptunes, and also from ground-based transit surveys, so from TESS and also from K2, where here again we're looking to refine the photometry for all types of planets. As I mentioned, 20% of the observing time is given over to the guest observers program. So performance-wise, KAOPS is doing extremely well. The measured performances are in line with those that were expected, the requirements, and in fact we're exceeding these performances. So looking to the plot on the left-hand side, we see noise in ppm as a function of G-band magnitude, and here we have some noise, some precision measurements which have been derived from real observations. The dashed line is the photon noise limit, and here we see what the limits are for the requirements. For bright stars, we had a requirement to achieve 20 ppm in 3 hours, so that would enable us to be able to get a signal to noise of 5 on Earth-sized planets orbiting sun-like stars. And then for fainter stars, we had a sensitivity a requirement of 85 ppm in 6 hours, with a view to be able to get very high signal-to-noise transits, so as to characterize transits of Neptunes around K-type stars. So here we can see nicely that we exceed very nicely the performances that we were due to achieve. So here, looking to a specific example of the performances that we get, we look to the Nu-2-Lupi observations, which you will have heard about in Leticia's talk earlier in the meeting. And here we can compare nicely the measurements from TESS and those from CHAOPS. And here we see the CHAOPS measurements, where we achieve on planets B, C, and D in 4, 3, and 1 transit a very high precision. Quantifying this, we can achieve a precision of 15 ppm in 10 minutes on an individual life curve, and 6 ppm looking when we bin to 1 hour. So CHAOPS science is starting to come out quite quickly now. A number of papers have been published, are on the point of being published. The science of CHAOPS is very broad, covering a number of topics in exoplanet science, all with a view to following up on known observations of exoplanets, known exoplanets. So the science cases for CHAOPS include accurate sizing of exoplanets, so that is improving the mass-radius relationship for sub-Saturn mass planets, so that is getting very accurate and precise sizes. Doing first step atmospheric characterization by studying the phase curves of hot Jupiters and also other planets, and also in secondary eclipse, so looking at occultations also. We're also looking to study the exomoons and rings, so looking in detail for the features in light curves which allude to structures or objects around other exoplanets. There's also a discovery mode to CHAOPS. We're not just following up on known bright host stars hosting exoplanets, but also looking to discover exoplanets. And this we will do in a number of different ways, including through transit time variations. Then as a final category, we have a catch-all, which is an ancillary science, and looking to, and this covers stellar activity, studies of trans-Neptunian objects, and also eclipsing binaries. And here, listed on the left-hand side, color-coded according to the topic, are the papers that have come out already from CHAOPS. In addition to those listed here, there are around 14 papers in various stages of preparation going towards publication, and then on top, a couple that have come out or about to come out from the Guest Observers Programme. So the sky of CHAOPS is defined by the orbit. Again, it's a low Earth orbit with an altitude of 700 kilometers. As we can see here, the CHAOPS sky, it's very different from that of TESS. Here, the color code is from blue to orange, going from the lowest to the highest coverage. And by coverage, I mean an indication of the fraction of days, the number of days for which a position on the sky can be observed per year with less than 50% interruptions. And here we go from 75, of order of 75 days for the orange colored regions, down to around 50 for the green area here. So the photometric performances are met or exceed even those that were required for targets which are between magnitudes of 6 and 12. For fainter stars, the limiting contributors are from the background contamination, from hot pixels and from cosmic rays. Looking towards the limits of CHAOPS for targets which are fainter than about G magnitude 13, a 1 meter ground-based telescope gives an equivalent precision. So one has to think carefully about the science case for such an observation. For brighter targets, for G and magnitude much brighter than 6, one needs to think carefully about how to avoid saturation. There will also be the impact of smearing trails, which are not currently taken into account by the data reduction pipeline. CHAOPS has a timing accuracy and precision of better than 1 second and 0.3 seconds respectively, which gives a good feeling for what we can achieve in terms of TTV observations. There are some systematics in the CHAOPS data, and these are primarily correlated with the roll angle. These include stars in the field of view and smearing from bright stars, both the star itself and also the the target star itself, and then also the stars in the field, but also from Earth's stray light. Pointing jitter has an impact on the KAOPS data, as does the telescope tube temperature, which is known as the flux ramp issue, and also there's potential issues with hot pixels. We see the effects of internal reflections on some of the images that we collect with KAOPS, and these are due to optical reflections within the telescope. Most of the above are corrected by the data reduction pipeline, about which you can learn more in the paper, which is mentioned here by Sergio Hoya et al. And the team from Marseille and from Porto, or by KAOPS, which Pierre will tell you about more shortly. So looking towards the opportunities which are offered to the community on KAOPS, we can see that 80% of the time goes to the guaranteed time observing program and 20% goes to the guest observers program. This is ESA run and enables community access to KAOPS. It's a total of just under 1,600 hours per year, so of just under 1,000 orbits per year. So this time is split 75%, 25% between annual calls and a discretionary program which runs throughout the year. So the guest observers program as a whole is open to anyone, to everyone, regardless of nationality or institute. The proposals are selected based on scientific merit and the applicability of KAOPS. We have a independent time allocation committee and chair, which is made up of scientists from ESA member states and who are appointed by ESA to these tasks. All data which is collected by KAOPS is pipeline processed by the Science Operations Center in Geneva. It's a pipeline which is not available to the community per se, but as mentioned, is the same that is used by both teams, by those from the guest observers programs and by those from the guaranteed time program, so the KAOPS science team. The majority of KAOPS observations will be time critical, looking at transits or occultations, but non-time critical observations are very much welcome, as these are easy to schedule and are very good fillers to improve the efficiency of the satellites, or the time we're able to spend on source. These are ideal for example, monitoring stars, looking at stellar activity. Coordinated observations are possible, so simultaneous with other facilities. This takes quite some scheduling coordination. As I say, it's possible, can be tricky, and cannot be guaranteed, as is of course the case for all time critical observations. There are tools available to assess target visibility, the sensitivity and precision that we're able to achieve with KAOPS, and also the observing time requirements that are needed to complete your any observing proposal. Should note here that the line of sight to targets in other active programs are reserved or blocked. So if a target is already proposed for science from an ongoing guest observers program or a program from the science team, it cannot be proposed by others, or it cannot be taken in a proposal by others.
Okay, we're over time. Do you want to leave this up?
Yep, indeed. I should say the next call is foreseen to come out in November. And then the discretionary program this is an important one. There's a single target newly discovered or declared to be of high scientific interest, with this requirement waived for PhD students or early career researchers. So this is a nice opportunity for people at the early phases of their career to get some time on KAOPS. And I leave you with a slide which includes the web pages which are particularly useful for the guest observers program, community web pages, the KAOPS data web page, KAOPS in the literature, and the mission archive, which is a very useful tool, not just for getting proprietary data, but also public data. And KAOPS data is now starting to become public. So there's already quite a bit which is available. So with that, I say thank you, and invite any questions that people might have. Very quick whistle stop tour.
So we'll do the questions in Slack because we're out of time there. But feel free to post any questions in the KAOPS chat, or in the KAOPS channel on Slack for Kate, and she can answer there. And also, if you want a more longer overview, then check out Willie's recorded talk on Friday, which is part of the Future Missions panel. And he'll give a little wrap up of that as well. Okay, so we'll move on now to Pierre Maxted, who's going to tell us a little bit about PyKops, which you heard about there, and about how to do data analysis using PyKops. So take it away. We can't hear you.
There you go. Thanks, Hugh. So this is just a very quick advertisement just to let you know that the KOps data analysis tool PyKops, which I've been developing for the science team over the past few years, is available for everyone to use. It's an open source software package. It's specifically written for the analysis of KOps light curves, and so it has functions and tools in there for characterizing the noise and for dealing with these internal reflections and roll angle correlated noise and so on. It's a pure Python package, so it runs on Windows, Mac, Linux, and it's straightforward to install. Just do pip install PyKops, and then if you've got an up-to-date Python 3 installation, it should just be available to you. It includes examples and a cookbook. So enable you to get started. A cookbook written by Tom Wilson is very useful to get started. The algorithms and models within PyKops, which have been developed over several years, are all described in a paper that's been submitted. In fact, it was submitted 2 months ago. We're still waiting on the referee's report, but all the gory details of the fancy maths underlying our decorrelation algorithm and so on will be fully described in that paper. And there's an active user community, and you're not required to use PyKops to analyze KOps data. Not all the science team does, but there are people who do use it on a day-to-day basis, and you can contact all of us on the PyKops Google Groups mailing list. And the models that are inside PyKops, in particular, the very fast Q-Power2 algorithm that's a very fast and effective and accurate transit model, are available as these LMFIT models. LMFIT is a Python module that does a lot of this sort of painful parameter handling, data plotting type stuff. So those can all be accessed. So if you're familiar with building your own likelihood functions and want to use the PyKops models to analyze data from test plus KOps, that can be done as well. Yeah, and I'm available to answer questions if you want to email me or contact me through the Slack to ask questions about it. I think that's it. Thanks.
Thanks, Pierre. Yeah, it's definitely worth using PyKops if you have some KOps data to reduce. Okay. Well, to make up some time, we'll move straight on to the science part of the talks. But what you can always do is drop a question to Pierre in Slack, or to Kate, of course, and to any of our upcoming science speakers. So I'll pass this over to Matthew Hooton, who's going to be the moderator for the science talks. Do you want to introduce our first talk, Matt?
Great, thanks, Hugh. Oh, hi, everyone. I'm Matthew Hooton. I'm a postdoc in Bern, primarily working on KOps data inside the GTO. And I'd like to thank all of the organisers of TSC2 for putting together such an excellent programme of talks that we were indeed able to splinter off from. And I think in turn, we've got a pretty excellent set of talks for you, exploring a range of synergies between the TESS and KOps missions. Each of the 6 science talks will last for 12 minutes, followed by 3 minutes of questions. When there are 2 minutes left, if you happen to see me in your gallery of people, then you'll see me do this. And if you go to the end of your talk, then I'll mention it like over the sound. And if you keep on talking much longer, then I'm going to have to start talking over you, I'm afraid. All right, let's get going. Without further ado, our first talk comes from Adrien Leleu at the Geneva Observatory, who will be describing a unique system of 6 transiting planets and a chain of Laplace resonances. Do you want to take over, Adrien?
Hello. Yeah, can you hear me?
Yep.
Right. So yeah, so thank you for the opportunity to present this work. So it's an illustration of the TESS KOps synergies. So I will talk here the example of the discovery and characterization of the TOI 178 system. So there are many contributing authors to this study, and also contributing instruments, so TESS and KEOPS, but also Espresso, Speakers, and GTS. So it all started in like August 2018 in the test sector 2 observation. So for TY178, there was 3 candidates announced, one at 6.5 days, one at 9.9, and one at 10.3. And yeah, we had a look at this system in more detail in a publication in 2019, and we found the same solution. So there was like 4 transits of the 6.5 day candidates. So here in purple, 2 of the 9.9 day candidates here in orange, and 3 of the 10.3 day candidates here in blue. So as you can see, these 2 planets are very close orbital periods. So there are bodies in our solar system with close orbital periods as well. And so those are the satellites, the Jupiter Trojans. So asteroids that liberate 60 degrees in advance or behind Jupiter in orbit. And you can actually have exoplanets on this, you can have planets on this kind of orbits, so on this sharing the same orbital period on average. But if so, then you would also expect to have large transit timing variation, because yeah, the planets perturb each other's orbits, so you will not happen to have transit at fixed period, but you could have variation. So that's something we should be able to observe to confirm those configurations. So yeah, that was quite interesting to have those candidates. So there's a situation, summer 2018 test sector 2 observation. We had a 9.9 day candidate with 2 transits and a 10.3 day candidate with 3 transits. So we had ground-based observation, so with Speculoos and NGTS. And in autumn 2019, we had observed 2 windows, one of which we saw the transit of 10.3 day planets, and one of them of it we didn't see it. So since we were expecting transit timing variation, we that was consistent with this for the observation. Then there was the Espresso measurement. So we had about 45 radial velocity measurements in winter between 2019 and 2020, which was also, the signal was also consistent with this co-orbital motion for the outer 2 candidates at around 10 days. So then we wanted to confirm this configuration. So the first idea was to have more radial velocity point, but it was not possible due to the pandemic. So this is the picture we had in spring 2020. Reanalyzing every data we had from TESS, Speculoos, and GTS and Espresso, we had additional candidate at 1.9 day, also at 3.2 days, and then we have the 6.5 day candidates and the two planets around 10 days, and then outer signals around 15 and 43 days that only appeared in the TESS data, in the Espresso data in radial velocity, but that were close to activity signals. So we are really unsure of those. So the strategy we choose to go for with KEOPS was to observe for 11 days. And the reason for that is that we expected to have large TTVs, so transit time variation, for the 10-day candidates because of the nature of the co-orbital configuration. So we wanted to make sure to have at least a transit of each, so we observe for 11 days. That's the observation conducted by KEOPS in August 2020. And here's the light curve we got by this 11-day observation. So the first thing is we could find the 2 transit of the 6.5 day planet where we were expecting them. But then we only had a single event that would correspond either to the 9.9 or the 10.3 day planet. So initially we thought it's probably more the 10.3 day planet because it's the one we saw transited 3 times in the test sector 2, but not, and the 9.9 we also only saw 2 transits. However, when we compared the different models, trying many different possibilities and reattribution of transits, it came out that it was most probably a transit of the 9.9 day planets, and that's the 10.3 day planets were actually an alias for a 20.7 day planet. So, and we also saw in the KEOPS the confirmation of the hints we had at the 1.9 day and 3.2 day planets as well. So yeah, it means that this transit here that happened almost exactly between the 2 transits of the 20.7 day planet belongs to something else. So it's quite unlikely. On timing alone, there is like a chance in 1,000, and it's also an event that has similar depth and duration. So that's quite puzzling, but it is how it is. looking at the orbital period of the planets, we can start to like study the architecture of the system. And we can see that these 4 planets here have, if you just take consecutive triplet of planets, what's called a Laplace relation. So there is a mean motion resonance between triplets of planets in the system. And so the system is close to an 18 to 9 to 6 to 4 to 3 resonance chain, where inner planet makes 18 orbits, the second one makes 9, the third one makes 6, and so on and so forth. So it's a more complicated version of the Laplace resonance of the Galilean moons of Jupiter, when Io makes 4 orbits, when Europa makes 2, and Ganymede makes 4. It's a more complex configuration with 4 planets. All right, so now that we identify this architecture, this peculiar configuration, which is the Laplace resonance chain, we only know 4 other multiplanetary systems that are in this kind of configuration. So that's quite rare. So now that we know that, can we use it to explain what happened there in what we initially thought is a transit of the 10.3-day candidate? So let's do the basic approach, which is we take our light curve, everything we have, so TESS, NGTS, CHEOPS, and we remove the models of the 5 planets we know, and we study the residuals. And this is a BLS, so we look for a periodic signal in the residuals to try to identify an additional candidate. And we can see there's 2 peaks, one around 13 days and one at 15.23 days. But these 2 peaks are constrained by data in summer 2018. So there's a 2 years propagation. And so a large error for the timing of these potential additional candidates. So, but if we consider the fact that the system is in a chain of Laplace resonances, and we use it thinking, okay, maybe this additional planet is also in the chain of Laplace resonances, and we can use the relation I introduced earlier. And that yields 2 possible periods for this additional planet, one around 30.5 days and one around 15.23 days. And as you can see, the second peak in height here also appears in the possible planet orbits that could fulfill the resonance chain. So we decided to go for it, especially because since now this period was not constrained on the fits of 2 transits that were in 2018, but were using the precision we had on the period on the 9.9-day planet and 20.7-day planets, because we observed them both in 2018 and 2020. We now had a very good precision of the period. So we planned this observation for the 3rd of October 2020, and that actually the time where the first collision avoidance maneuver were done for Cheops. So yeah, so the data transmission was delayed by several days. But we finally got it, and we could confirm the presence of these 15.23-day planets at a period which is very close from the one we could predict from the architecture of the system, the resonance state of the system. So that gives a very good example of the capabilities of prediction from orbital dynamics as well. So starting from test sector 2 and a lot of effort from ground-based observation and more than 11 days of continuous observation from Cheops, we could achieve a 6-planet system with a chain of Laplace resonances. And as I said, it's now a part on the only 5 systems we know in this kind of configuration. So you can also hear how the resonance sound. Yeah, you can find a longer version on YouTube. So now that I briefly described how we could reconstruct the orbital architecture of the system, I want to talk a bit about the densities of the planets. So in theory, the basic theory for the composition of planets will tend toward having planets that are closer to the star to be more dense. So here, a larger equilibrium temperature, more dense planets. Why is that? Because planets form closer to the star are expected to form with more rocky materials, and also are more subject to photoevaporation, so tend to retain a more terrestrial nature close to the star and more gaseous outside. And it's also something we can see in the other system, which are in chain of Laplace resonances. Why is it interesting? Because this configuration, the chain of resonances, are very fragile. So we assume that they didn't change much since their formation. And so if you have a system which is roughly untouched since the formation, and you can see that it all follow this theoretical trend to have more dense planets closer to the star. So now we had Cheops observation to refine the radii of the different planets. So you can see here on the left the observation of each planet by TESS, here by Cheops. And we can see that we can achieve a very good precision on the radius of about 6% for the smallest planets inside the terrestrial one, and about 3% down to 3% for the outer ones. We also had 45 radiodiversity points. 45 radiodiversity points is not a lot for a system of 6 planets, sorry, but thanks to the transits, we had very good constraint on the periods and phases. So that allowed us to constrain the system enough so that we could get a mass estimation. And so that we had the radius and the mass, we could estimate the densities and do internal structure modeling. So this is the result of our model for this system. So as previously said, we have 2 inner planets that are rather terrestrial and more gaseous planets outside. What's very interesting is that you can see there is a large variation in the fraction of gas. So gas is gray, blue is water, and brown is rocks. And yeah, we have like very dense, very fluffy, planets in planet D and planet G, and more dense planets in between. So this is very surprising. If I take back the previous plot I showed with the theoretical trend and plot here in red COY 178, you can see that there are actually variations of densities within the system. So if we had another kind of system in this...
15 minutes, Adrian.
2 minutes?
No, we're at 15, sorry.
Okay. So, yeah. So we can see that there is large variation of densities in the system. So which is at odds with the fact that the system is very well ordered. Yeah, so the TESS Cheops synergies. So TESS identify multiplanetary system. We can then refine radii with Cheops and help solving the architecture by solving potential misattribution of transits or aliases. And the 2 satellites can work together to solve TTVs, transit time variation, to better constrain masses and eccentricities. Thank you very much.
Thank you, Adrian. We have one question in the Slack channel. Hugh asks, does the 43.7-day signal from the RVs correspond to the Laplace resonance, and does it transit?
So it's nearby. It's okay. So the peak in the radial velocity is quite broad, actually. So that's sorry, that's an interesting question. So the peak in radial velocity is quite broad because our date coverage is not that big. So you can move it around so it's fall inside the Laplace resonance, yes. But as I said, it's close to an activity signal, so we cannot be sure it's actually a planet yet. I would say the bad news is that the system is very flat. So this is the inclination of the different planet we know. And if we look at the impact parameters and scale it with respect to the distance of the planet, we can see that if the planets, another additional planet, have a period above 26 days and is in the same plane than the other planets, then it will not transit. So yeah, if there is this additional 40-day planets, which is in the chain, if it's in the same plane as the other, we should not see it transiting, but that's why it's interesting to continue monitoring the system in radial velocities, but also in TTVs to try and see if there is additional system in the planet. And what's also very interesting is that if there is an additional planet around 40 days in the resonance chain, it will also be inside the habitable zone around this planet. On this system.
Yes. Yes, it'd be very nice to kind of round this system off with something that falls in the habitable zone. So we'll keep an eye out for a very short grazing-like signal at 45 days and see if we're lucky. All right, thank you very much, Adrian. We'll move on to the next talk. So next we have Antoine Thuillier, who will describe the results of a transit survey searching for planets around hot subdwarfs. Are you there, Antoine?
Yes. Okay, so let me share my screen. Oh. Can you see the screen?
Yep.
Yep.
Okay, good, thank you. So I will present you my research project, which is called a transit survey to search for planets around hot subdwarfs. And I will start with a bit of context. After leaving the main sequence, most stars go through two giant branches, the red giant branch and the asymptotic giant branch, before becoming white dwarfs. And during both of these phases, they dramatically expand, and by doing so, they remove all near orbiting objects by either engulfing them or evaporating them. And the question is, what happens to these bodies that are either engulfed or, more globally, to the planetary system after the red giant branch? So far, there's no observational constraints for engulfed planets, so we do not exactly know what could be the remnant of such a process, even if we suppose it should be the core of previously giant planets, so they should be around few Earth radii. Then there is no occurrence rates for planets right after the red giant branch. But this can be settled by observing post-red giant branch stars for planetary remnants. However, this is not possible with most evolved stars, as they are too big for our current technological means to allow the detection of such small bodies as could be the remnants. Luckily, there's a type of stars that allow us to do that, which is hot subdwarfs. But what are hot subdwarfs? These are stars that went through the red giant branch, but during this phase, they lost most of their envelope, which prevents them from ascending the asymptotic giant branch. So they lie in what is called the extreme horizontal branch to the left of this diagram. And these hot stars, what is important with them is that they are small, between 0.1 and 0.3 solar radii. So for such small stars, our current technological means allow for the detection of small bodies such as the remnants of planets. Also, there's no confirmed planets around them, even if several have been claimed, none of them have been confirmed. We also have a large and recent data samples that are available thanks to the missions Kepler K2 with few targets and very high precision, TESS with a large number of targets and good precision, and Cheops with few targets and high precision. TESS makes the bulk data for this study as it covers a large part of the sky, while Cheops will be very important in another part of the talk, as I will highlight later. So overall, this makes between 2,000 observed hot subdwarfs for short cadence mode and up to 5,000 when all cadences are considered, which is a pretty big sample. I performed the analysis by first looking for shallow transits using the pipeline we developed called the Sherlock pipeline, which stands for searching for hints of exoplanets from light curves of space-based seekers, that we present in a paper published last year. The pipeline is on open access, and its main missions are to first gather the data, then clean it by applying several detrendings, and search for transits according to the parameters the user wants. The last part is to display the results. You can see here an example of a result. On the top panel in gray is the light curve, the detrended light curve, and in red, the position of the transits of the selected signal. The middle panel shows a folded phase of the transits with in red the model, in orange a binding of the data that appear in gray. So you can see that this signal is pretty clear with a signal over noise ratio near 40. Then the last panel is a parallelogram of the signal where you can easily see the harmonics. This signal is actually not a planet. This star was labeled as a hot subdwarf, but our study showed that in fact, it's more likely to be a combination of two stars, subdwarf of type F, along with a star from the blue horizontal branch. Then some stars display an important variability. And for them, we use the pipeline called Felix, developed by Stéphane Charpinet, which is designed to detect stellar variation. And we use it to remove them from the light curve. You can see here an example. In blue is the original light curve, and in red, the cleaned one with Felix. And there's a shift on the blue one for visual purpose. So we go from a root mean square of nearly 10,000 to only 500. But by doing such a process, we need to be sure that we do not remove the transits. And so to do so, and also to be sure that all the processes do not remove planets, we perform injection and recovery tests to infer the light curve quality and the size of the bodies we can expect to detect. And to do so, we use a pipeline we also developed called Matrix. And the injection and recovery test consists in taking a real light curve, injecting a synthetic planet with given parameters as radius and period. Then we detrend the light curve and try to recover the signal. And by repeating this process a large number of times, with a variation of radius, period, and the epoch, which is the first time the transit appear in the data, we get this kind of graphs where in yellow, all those planets that have been inserted here have been recovered, and in blue, none of them. The axes are here the radius, and here the period. And this helps us to understand other parameters that can impact our research. Here you see 4 different stars that have been tested by this method. And the difference is their magnitude. The first one has a magnitude of 10, then 13, 14, and 15. And you can see that the difference is pretty clear. And most of the stars from our sample have a magnitude between 13 and 14. So these two. And you can see that for such stars, we are able to detect planets down to 2 Earth radii, which is exactly what we are looking for as suspected remnants from an engulfment of a giant planet. I mean, should be of around few Earth radii. Then we perform follow-up observations using either TRAPPIST or KEOPS or radial velocity measurements. And this is where KEOPS is a key tool for this research, because TRAPPIST cannot confirm all the signals we are looking for, because they are either too faint or too shallow, or not in the right part of the sky. While KEOPS has a wider field of view and a greater precision. So this is where KEOPS is a really useful tool here. Then we compute post-red giant branch planetary occurrence rates. So the current status of the study is that the cycle 1 of tests is now fully analyzed with promising results, which represent approximately 800 stars. And we recovered numerous bodies such as TOIs, but also white dwarfs and brown dwarfs transiting their host star. And among the 800 stars of the cycle 1, I identified approximately 200 potential signals that were worthy for more investigations. So most of them were not really clear, but worthy for more investigations. And among them, 25 are really promising, and these are the ones that need that are under follow-up observations, while 60 are still to be investigated a bit further, and the others are either discarded or the investigations have been stopped due to them being not good enough to invest more time. So the next phases of the study will be the continuation of the analysis of test data with cycle 2 and 3, on the fourth one when it will come. The follow-up of the promising results of the promising signals, with KEOPS and TRAPPIST, as well as the analysis of the data from the mission Kepler and K2, along with the analysis of the long cadence modes. So to conclude, the question is what happens when a planet is engulfed by its star, or more globally, what happens to a stellar system after the red giant branch? Hot subdwarfs are pristine candidates to help us settle this issue because they are small on post-red giant branch stars. And we already explored 800 of them and unveiled several interesting results that are under follow-up observations. Also, if there is no detection in this study, it would allow us to put strong observational constraints of the survival of planets. And due to the large sample of stars, the statistic we could derive for that would be meaningful. But if there's a detection, it would be the first confirmed planet around the hot subdwarfs and a potential survivor of an engulfment, which would be pretty big. Then we have all the tools to settle this important issue, thanks to the missions Kepler, K2, TESS, and KEOPS, which represent several thousand of hot subdwarfs that have been observed. And we have powerful tools to perform the analysis with the pipeline we developed, as well as easy access to follow-up observations, thanks to TRAPPIST and KEOPS. So as clearly 2020 was not enough, what we really need now is zombie planets, and we plan to bring them in the game. Thank you for your attention.
Thank you, Antoine. Very interesting talk. There's a few questions and comments in the Slack channel. First one from Diana. She says, I understand that if we don't search, we won't find, but do you have a sense of how often planets could survive the cast off of the star's outer layers, or is the idea that the planets would form outside or exterior of those layers?
Okay, so there's several possibilities. We do not really know the proportion of planets that could survive such an event because, as I said so far, there is no confirmed planet that went through this process. But we start from the occurrence rates of planets like giant planets orbiting near a main sequence star. And we derive that to the number of hot subdwarfs we observe. And for 2,300 hot subdwarfs, accounting for 1% of solar-like stars have hot Jupiters, which would be the planets that are the most expected to survive. And a transit probability below 1 day of 10%. It means that if they survive, we should have, there should be 23 hot subdwarfs in the sample that have had a hot Jupiter, and 2 or 3 of them should transit. So it's not much, but when taking all the sample with 5,000 hot subdwarfs, it's 5. So if they survive, we have a chance to detect 1. But it's not, as I said, it's not sure that they survive. I mean, it's even the contrary. It's likely that they do not survive, which is why I put here that it's also an interesting result, as we could compute meaningful statistics for the survival of planets if we detect none in such a large sample.
If we have time for one more question, Matthew, I don't know how we're doing for time.
We've still got a couple of minutes or so.
Okay, I have a question for myself, kind of leading on from that. Due to the mass loss of the star during the RGP phase, wouldn't we expect planets to move radially outwards in their orbits, and so therefore the probability of seeing them transit and/or I guess be engulfed might decrease?
I'm not sure to understand. You mean the mass loss should expel planets instead of engulfing them?
Well, potentially, right? As the star loses mass, then yes, the angular momentum of the orbiting planets might cause them to drift to large orbital periods, right?
Yes, but there is also other effects. I have a graph for that that lead the star to spiral inward. The planet to spiral inward, and so to be engulfed by the star, and then it could evolve in the less dense layers of the star, while still spiraling inward due to the friction. Yeah. So as for hot subdwarfs, this red giant branch phase of engulfment should be shorter due to the expelling of the outer layers of the star. It should still be able to, well, the engulfment should still happen and let the planet to live, possibly. I mean, it's not sure at all.
Great, thank you very much, Antoine. Perhaps at the next Test Science conference, when we've got more test data and perhaps more KEOPS data, you can come back and present an update. All right, so we'll now move on to Dominic Otto, who will describe an effort to characterize small planet candidates with TESS and KAOPS observations. Dominic?
Sure thing. Hello, everyone. I am going to take the screen sharing. And hopefully I can just get one thumb to see that I've got the right presentation on this great.
Looking good.
So yes, hello everyone. My name is Dominic Otto. I'm a graduate student at the University of New Mexico in Albuquerque, New Mexico. And today I'll be presenting an analysis of 5 systems which were jointly observed by both TESS and KAOPS. These targets include TOIs 262, 444, 455, 470, and 560, and together they represent a sample of small planets with precise radius characterizations. So first I'll begin by motivating observations of these planets, then discuss steps taken to analyze the light curves for these targets, and then discuss actually each target a bit more in detail, and then conclude with some other considerations and future work. So to begin with motivations, these particular targets chosen for this study had calculated radii between 1.3 and 4.6 Earth radii prior to their observations by KAOPS, but these values were poorly constrained. And it is well known, of course, that a histogram of confirmed planet radii shows a bimodal distribution with a value between 1.5 and 2.0 Earth radii, as shown by figure 5 from Fulton and Petigura 2019. We can see this nice bimodal distribution. And this calls into question multiple theories constraining planet radii, which includes photoevaporation and core-powered mass loss, I believe are the 2 main ones. And if this particular value is found to be real and not a product of systematic biases, this will yield photoevaporation as the dominant mechanism sculpting planet radii. So precisely measuring the radii of more planets is important for both confirming this trend, but perhaps more importantly, this is an important step to finding planet bulk densities, which will allow us to build and test theories of planet composition. And given the fact that density depends on volume, which in turn depends on radius 1 over cubed, that means that there's a very strong correlation or dependence on planet radius, which is why it's so important to have a very precise value for the radius. So with that being said, these particular KAOPS observations were completed between October 2020 and January of 2021 under the KAOPS Guest Observers Program with the observation ID 125903. The KAOPS data reduction pipeline provides many data products for the user, including various iterations of the light curve computed with different aperture sizes. So for each of these targets, we use the optimal light curve, which is determined by calculating the signal to noise ratio at various aperture sizes. And then both time series between the KAOPS and the TESS light curves that I used were converted to BJD to ensure a common time frame. So then moving on to detrending, the KAOPS light curves, like any other, must be detrended for background noise, position on the aperture, and other variables. The KAOPS telescope, as we heard earlier, rolls while pointing at the target, which means that background stars rotate in the telescope and must be detrended with respect to telescope roll angle. So the detrending that I did was completed using PyKAOPS, which Pierre shared earlier. And I introduced individual detrending parameters and calculated the Bayes inference criterion for each one to determine whether the parameter was actually necessary for the model for that particular target. And that was done in an effort to prevent overfitting. And then shown here is the KAOPS light curve with a test transit model for TOI 444 before and after detrending. And we can see that some of these systematics have been removed. So that looks nice. And then from here, I used Batman for the transit model, with fixed limb darkening parameters. And then I simply used MC to find the best fit parameters for that transit model. So then, just kind of moving into the next actual results part of this, I'll kind of detail each target by describing the fits for the test data, the KAOPS light curve in the middle, if you're following my cursor, and then the joint fit on the right, which comprises both data sets at once. And so for the KAOPS light curves, I fixed the period because I fixed the period to that reported by the TESS transits because since there are multiple transits for the TESS light curves and only one transit for KAOPS, the period will obviously be more precise from TESS. So then something else is that all of these fits are for circular orbits and eccentricity was set to 0. So I'll try to highlight whether any values are discrepant or just kind of highlight some values that came out for each of these fits. So TOI 262 is a late G dwarf with the stellar temperature and radius as shown in the bottom right here. And we report no discrepancies in this data set, but I will note that the error bars on the fit for the KAOPS model are larger than those for both the test data and the joint fit. And the period shown here is 11.145 days with a planet radius of 2.32 Earth radii. So then moving on to TOI 444, again, we have the phase folded test data around the transit, the KAOPS light curve, which looks beautiful in my opinion, and then the joint fit for this model. And again, there are no discrepancies here. TOI 44 is a nice K star with the following stellar temperature and radius. And the period of this planet's orbit is 17.964 days, and it has a radius of about 3.1 Earth radii. So that looks nice. Here we have TOI 470. It's another K star based on its temperature and radius. Here again, it looks like a very nice transit in the test data, and we also have the KAOPS light curve as well, and then followed that up with the joint fit parameters. And the period that comes out of this one is 12.19 days, and it has a radius of 4.2 approximately Earth radii. Moving on, TOI 560 is a cool K-dwarf, which exhibits some very nice looking transits. I know it, maybe I keep saying that a lot, but these are some very nice transit models. So they're looking good to me. Yes, so it's got the stellar temperature and radius here. It has a period of 6.4 approximately days, and it is about as big in terms of radius as 2.794 Earths. So that system looks good. But TOI 455 is where the pedal kind of hits the metal, if you will. We've got some very noisy test sectors, as you can see in this phase folded data, but some very good looking KAOPS transits. However, given everything that's here, the fits gave me discrepant radius ratios for these light curves. And then that also means that the joint light fit is somewhere in between those two. And that also makes the impact parameter for this planet discrepant as well. So that there's something else going on here. And that's where Winters et al. Comes in. In 2019, they reported the discovery of this planet, and they found that this is a nearby triple M dwarf system that is hierarchical, as shown in this plot on the upper right here. And they're all blended in one test pixel because test pixels are pretty large. So that might explain why the test transits are quite noisy. A small table of their reported values are shown in the bottom right with values that are different from mine, highlighted in red again. So given that the size of a KAOPS pixel is 1 arcsecond, KAOPS should be able to physically resolve A from BC. Hopefully you can see the subarray animation in the upper left there, and you can see the kind of two targets twirling around each other. So that means that there's a potential blending scenario here. And I couldn't quite figure out in time. The thing is that the DRP light curve for KAOPS is about 15 pixels at a minimum. And that means that the entire triple star system is convolved into the KAOPS light curve. And something that I'd like to do in the future is create my own aperture with KAOPS pixels in order to precisely pick out the A from the B and C targets. So work on this one is ongoing. But with all that being said, we've got very precise radius estimates for all of these targets. So what we did was we calculated the radius based on the radius ratio and the stellar radius and propagated uncertainties from that to give the error bars for each target. And we can see that precision is improved for each of these targets prior to what they were. And we also note that none of them fall within the radius valley from 1.5 to 2.0 Earth radii. So that's an important result. And then additionally, I want to examine the transit depths and their uncertainties for each of the different fits and each of the different targets. So it's notable that given that this tells us about the relative photometric performances between TESS and KAOPS. And since we were fitting at most 8 TESS transits, and the precision on the KAOPS transit depths should be better than that for the TESS transits, since the KAOPS
2 minutes to go.
Sorry?
2 minutes to go.
Okay, thanks. So yeah, that means that since KAOPS is about 9 times larger, that means that KAOPS should have a better photometric precision. However, we see improvement in transit depth uncertainty for only TOI 444. So the specific causes for that are also to be investigated. But just to wrap up on some science, another important method which may distinguish between models of planet formation is a period radius diagram. This is from Fulton and Pettigura figure 6 on the left. But while our currently analyzed samples, which are the large blue stars, is not yet large enough to draw new conclusions regarding planet formation mechanisms constraining planet radii, we note that with the inclusion of KAOPS observations on 7 more planets, which hopefully those are showing up as the small blue stars scattered around the plot here, it nicely populates the 2 sides of the radius period valley. And with precise KAOPS radii, we aim to obtain better constraints on the edges of this valley and hopefully will help to differentiate between different origins of this valley. So then just to quickly wrap up today, I'll talk about future work. I'd like to resolve that TOI 455 dilemma that I discussed earlier. I would like to investigate whether the precision on the KAOPS transit depths can be improved further. And I also would like to investigate possible TTVs, especially for TOI 470. So with that, that is the bulk of my talk, and I'm open for questions. Thank you for your time.
Thank you very much, Dominic. That was a very interesting talk. You're more than welcome to say how amazing the KAOPS slide curves are. It's fantastic to see these higher efficiency observations out in the wild. So we have a question in the Slack channel from Will Meisner, who says, on your earlier slides, it looks like some of your TESS and KAOPS radii, TOI 470.01, I think, and a couple of others, were different by many sigma. Do you think the radius uncertainties are bigger than reported for your planets? But maybe he's misreading.
So I will say that given the sigma that I calculated, the radius ratios, just taking 470 as an example, do agree to within 1 error bar of one another, at least within that. So perhaps I've been reading it wrong, but as far as I can tell, they mostly agree. As I said before, the one that doesn't agree within error bars is TOI 455, that small hierarchical M dwarf trio. And then, a nice way to kind of look at that is the error bars on the radius estimates shown here. For the most part, all agree except for TOI 455. So hopefully I haven't been reading it wrong, but yeah, good check on that. Thank you.
Yeah, 455, that looks a bit tricky. Maybe PSF photometry or something could help out with that.
We still have a couple of minutes or so. So I'm just going to make an assumption. Is the reason you're going to explore TTVs for 470 is because it arrived very early in your light curve?
Indeed, yes. So that is a potential discovery that we're hoping to look into more in the future. As you can see, it is only a partial transit. We didn't get the ingress of the transit. So yeah, that's a possible transit timing variation that we want to investigate.
Yeah, that's interesting. I mean, that would, well, yeah, it looks like it'd be of the order of like almost an hour or so if we assumed there was like no real like ephemeris drift that would cause that sort of like difference. And another one, I noticed that a new planet has recently been detected for 455, which I guess was already your tricky one.
Yes.
Did you have plans to perhaps follow that one up further as well?
Yes, I just learned about that paper yesterday, and I am hoping to incorporate that into the analysis. But again, since analysis on TOI 455 is going to continue anyway, I definitely hope to take a lot more time and very carefully examine all of the light curves that I can possibly get my hands on for this target. And then, like I said, most importantly, I want to create my own aperture with KOPS pixels to kind of just nicely pick out just the A from that one. But yeah,
Yes,
definitely something to look into.
Yes, taking your time is never the wrong approach for this sort of thing. I mean, people who have been in this for a while know exactly how difficult trying to combine data sets from different instruments is at times. So it looks like a really good job here. All right, thank you very much. We're now on to Amy Chewson, who will describe a search to find geotransits in test data suitable for KOPS follow-up observations. So take it away, Amy.
Hi, so my name's Amy Chewson, and I'm a second year PhD student working with Didier Queloz at the University of Cambridge. Today, I'm going to give you a summary of my PhD project. So in essence, I'm using two space-based telescopes, so TESS and KEOPS, to search for and follow up a unique type of transiting exoplanet signature called a geotransit. So during its 2-year primary mission, TESS observed the majority of the sky for only 27 days, as shown by the well-known sky map. So this means that any planet with a period greater than about 13 days would only have been observed to transit once in the data, if at all. And these single transit detections are known as monotransits, and they are abundant in the TESS data. Here is an example of one of these monotransits detected in 2-minute cadence TESS data. So if we can follow up these planet candidates by observing additional transits, then we have the exciting opportunity to discover longer period exoplanets than are typically found in TESS data. And this is really important because the currently confirmed exoplanet population is so biased towards short period planets. And this is illustrated here by the well-known period radius distribution of confirmed exoplanets from the NASA Exoplanet Archive. So I've highlighted discoveries made by TESS in pink here. So monotransits offer the potential to discover planets in this region here. So there's very few confirmed planets from TESS. And this would help give us a more complete view of the exoplanet population, and it offers the potential to find planets orbiting in the habitable zones of their host stars. So what's the catch with monotransits? Well, following up monotransits is difficult and can be very time consuming because nothing is known about the ephemeris of the planet candidate. Fortunately, TESS is re-observing the sky in its extended mission. Simulations have predicted that about 52% of primary mission monotransits will be observed to transit a second time. And the result will be a sample of planetary candidates with 2 observed transits separated by about 2 years. And these are what we call geotransits. So the plot on the right shows the results of the simulations. You can see that the periods of the geotransits extend right the way out to 200 days. So just like monotransits, following up geotransits offers the potential to discover longer period exoplanets. However, the follow-up of geotransits is more feasible. So although the ephemeris of the planet candidate still remains unknown, there now exists a discrete set of allowed period aliases. In this equation I'm showing here, T-diff is the time between the 2 transit events, and n is an integer. So n runs from 1, which would imply the period of the planet is the maximum allowed, right the way up to some maximum, which is dictated by the longest continuous baseline of the data. So in order to follow up these geotransits, you can target each period alias until another transit of the object is detected. In this way, you can resolve the ephemeris and confirm the planetary nature of the object. So with a T-diff of about 2 years, there are quite a lot of possible aliases for geotransits, but we can be clever about which ones to target first. So you can see in this plot here, I'm showing a simulated TESS geotransit, and the period aliases are on the right-hand side. And you can see each of these has an assigned probability. So as expected, the shortest periods have the highest probability due to the geometric effects of the transiting alignment. So these are the ones that we can observe first. Cheops is the perfect instrument to follow up geotransits in this way, with its targeted nature and high precision capabilities. So I'm a member of the Cheops Geotransit program, and our goal is to use the Cheops satellite for the targeted follow-up of test geotransits. So importantly, in order to be complementary to ground-based facilities, such as NGTS, we will only select targets for which space-based observations are necessary. For example, if the transit depth is very shallow or the duration is very long. So we already have a sample of test geotransits suitable for our program. These were all discovered as monotransits in the test primary mission, and then were observed to transit a second time in the extended mission. For example, the monotransit I showed earlier became a geotransit when the new data was released. The problem with this approach is that to be discovered as a monotransit, you need to have a relatively high signal to noise. And so the transit is typically quite deep. But as I said, the aim of the Cheops program is to follow up shallow geotransits. So we needed a way to discover geotransits more suitable for our program. To this end, I am developing an automated pipeline that will search for geotransit signals in the test primary and extended mission data combined. So by searching for 2 transits instead of 1, the signal to noise is boosted, and I should be able to discover shallower geotransit candidates to follow up with Cheops. The first step of this process was to select the stars that I wanted to search for geotransits. So I started with the full catalogue of 232,764 stars that were observed at 2-minute cadence by TESS in the primary mission. I then narrowed this list down according to several criteria. Most importantly, I required the star to have good Cheops visibility. Next, I selected stars brighter than a Gaia magnitude of 12. And finally, I selected dwarf stars smaller than 2 solar radii, because these are the most promising targets for planet searches. After these selection criteria, I was left with 84,288 stars that were suitable for my geotransit search. This plot shows the positions on the sky of all those stars observed at 2-minute cadence in the TESS primary mission. Those in red were ruled out of my geotransit search, and I will be searching for geotransit signals around those stars colored green here. So with the target selected, work then began on the pipeline itself. And I'm going to demonstrate how it works using a geotransit that I already knew existed. So here I'm showing its 2-minute cadence PDC-SAP light curve from the primary mission on the left and the extended mission on the right. So first of all, the light curve is detrended using a mean sliding window. The upper plot shown here includes that fitted trend in red, and the lower plot shows the resulting detrended flux. A box least squares transit search is then run on the detrended flux, with parameters optimized for geotransit detection. So this periodogram may look a little unusual, but that's because geotransits don't have a unique period, so we get peaks at the many period aliases. The absolute peak is highlighted in blue here, and it corresponds to one of the period aliases of the geotransit, and the corresponding in-transit data is highlighted here. In this case, the geotransit was already known, but normally, if the peak detection corresponds to a geotransit candidate, then a manual inspection is performed. This includes examining the 2 transit detections individually, as shown here, checking the TOI catalogue, and in some of the most promising cases, modeling the transits. So in order to predict what I expect to discover by running my geotransit pipeline, I used the simulation results from Cook et al. 2021. So firstly, I looked at the geotransits in the simulation. So I took the catalogue of stars used in the simulation, which is only for the southern ecliptic hemisphere, and I applied the same selection criteria that I used to produce my own stellar sample. This resulted in about 40,000 stars, around which there were 41 detectable geotransits. So I plotted these 41 simulated geotransits on the period radius diagram from earlier. However, these geotransits are around stars brighter than a Gaia magnitude of 12. So let's remove all the confirmed exoplanets around stars fainter than this. And you can now clearly see that the geotransits are standout targets. They're amongst the longest period planets around bright stars. So I expect my pipeline to return real geotransits within this exciting parameter space. I also use the simulation results to predict how many geotransits I expect to find in my stellar sample. And I predict that I will find about 45 geotransits in the southern ecliptic hemisphere alone. Now, I haven't run my pipeline on the full southern ecliptic hemisphere yet, but as a proof of concept, I have tested my pipeline on a small subset of stars. So I selected this subset from my full sample according to these criteria. So the star must have been observed in test sectors 1, 2, or 3. It must have been reobserved in the extended mission so far, and it must have 2-minute cadence data in every observed sector. This left me with 5,730 stars to run through my pipeline.
2 minutes,
So,
Amy.
what did I find? Well, the pipeline returned 750 possible geotransit candidates, and I manually inspected every one of them. So, as was to be expected, I found the majority of the detections were false positives, and there were a further 138 candidates that require some form of more sophisticated vetting. But most excitingly, I found 13 genuine detections, including 2 new geotransits. So I also recovered 4 geotransits that were already in the sample for the Cheops geotransit program. And this was all of the known geotransits from these sectors, so my pipeline didn't miss any expected detections from the stars that I searched. Also, the results of this trial run are consistent with the simulation predictions. So with a test stellar sample of 5,730 stars, I would expect to find 6 geotransits, and that is exactly what I have confirmed so far. So one of the new geotransits found by my pipeline is shown here. A preliminary fit revealed a transit depth of about 400 parts per million, making this one of the shallowest geotransits that we have in our sample so far. So this trial run has shown that my pipeline is capable of discovering test geotransits that are well suited to future Cheops follow-up. So I'll leave my conclusions here, and I'm happy to answer any questions. Thank you for listening.
Thank you very much, Amy. Very interesting talk. I think we probably have time for a couple of questions. A couple of short questions.
Okay.
Yeah, you're well within the time, so I think 2 questions is fine.
So we have one on the Slack from Gaia Lachadelli. Nice talk, Amy. How did, I'm glad you asked this because I was going to ask this one as well. How do you compute the exact probability of each alias? Do you also take into account the duration of the mono/geo transit?
Yes, so this is something that Hugh Osborne has a code for called monotools. So it's available on GitHub, and this code basically will take your data and you can tell it where the geotransit is, and it will output the period aliases with these probabilities. So it takes into account things like the geometric effects, and it also takes into account the duration of the transit. And I'm not sure if there's anything I've missed, if Hugh wants to say anything, but I think that's the 2 main things. And the kipping period prior as well, I believe, is the third thing.
Great. Another question from Diana. This is really exciting stuff, Amy. The original Cook et al. Predictions estimated 70% retransiting STPCs.
Single transit planet.
Single transit, of course. I'm not on my acronyms today. But you showed 52%. Do you know what changed?
Yeah, so it's in the most recent simulations from Cook. He's updated his occurrence rates that are what produce the planets. So he's used some more up-to-date ones for the, I think it's FGK stars, and that is what he says has changed these predictions. And I think it's a slightly higher fraction. So the 52% is the number that will become geotransits. And there are also some that will have more than one transit in the extended missions. There's slightly more there as well.
Great. Thank you very much, Amy. I look forward to seeing how this progresses when more data keeps rolling in.
Yeah, thank you.
So next up, we have Faith Hawthorne, who will describe the detection and characterization of 2 planets transiting the nearby K dwarf TOI 836. Do you want to start, Faith?
Yeah, hopefully everyone can hear me and see my presentation slides okay? Brilliant. Thank you very much for the introduction. So my name is Faith Hawthorne and I'm just coming up to the end of my first year of a PhD at the University of Warwick. And today I will be presenting the current progress of my work on TOI 836, 2 planets transiting a nearby K dwarf. So TOI 836 was first observed with TESS in April 2019. It's a fairly bright target with a TESS magnitude of 8.5 and a visual magnitude of 9.92. It's also a nearby target at approximately 89.7 light years and moves with a relatively high proper motion of 201.4 milliarc seconds per year. The transits of the 2 planets also display significant transit timing variations, or TTVs, roughly on the order of 5 to 45 minutes. The global modelling of our data is being done in the Exoplanet package written by Dan Foreman-Mackey. And firstly on the right, we can see the target pixel file with sources from the Gaia DR2 catalogue in TPF Plotter, with the aperture mask outlined in red and our star marked with a white X. And secondly, the KEK2 image, showing that there are no nearby blended targets that would affect our data. So we have numerous sources of both photometry data for transits and spectroscopy data for radial velocity. We have 2 sectors of TESS, 11 and 38, from year 1 and year 3 of the mission respectively, 5 observations from the KEOPS spacecraft, and many others from various ground-based facilities. These are complemented by short cadence spectroscopy data from HARPS, PFS, and Minerva Australis, which are folded into our global modelling, and long cadence data from the HiRES and iShell instruments, which may help us to constrain long-term trends in our data. First of all, we can see this plot from 2 of our summer students, Harvey and Tamsin, who are also working on the system. Our analysis of the transit timing variations is ongoing, as we still need to refine the planetary periods from TESS in order to remove this linear trend that we see on this plot. If the transits of the planets were strictly periodic, each of these data points would be expected to lie exactly on the line. But this shows that from a preliminary perspective, we do have TTVs in this system. But again, this is a work in progress, as we still have to consider each data set and fit our transits in a uniform way and refine our initial planetary periods from TESS. So why use KEOPS data to run our work? Well, TOI 836 is of sufficient brightness in the KEOPS observing band, recalling that it has a visual magnitude of 9.92. The durations of the planet transits are also short enough that continuous monitoring of the target is unnecessary. If the transit epoch is known, KEOPS will be able to observe a transit. The TTVs are also on a suitable and measurable order, again recalling that they lie between 5 and 45 minutes. Transits of planet B can be difficult to observe from ground-based facilities, as it is considerably shallower than that of planet C, making KEOPS a great space-based instrument for observations of the inner planet. The KEOPS transit data will also aid in further refinement of the planetary radii and other parameters in our global modelling fits of the system as a whole. Another advantage of the KEOPS observations is that they bridge the gap between the 2 TESS sectors, Sector 11 in year 1 and Sector 38 in year 3, with 4 out of our 5 observations being taken in mid-2020. KEOPS observes 4 transits of TOI 836c in sets 1, 2, 3, and 5, and 1 transit of TOI 836b in set 4. TESS's continuous target monitoring in each sector means it is able to observe transits of both planets. So first of all, we can see results from TESS Sector 11. On the left-hand side in the top panel, we see the TESS PDC SAP flux normalized to 0 and the Gaussian process, or GP model, for the photometry in green, which has been used to correct for the stellar activity. Below this, in the second panel, we can see the data with the GP removed and the transit models of planet B in orange and planet C in blue. Finally, we have the residuals on the bottom panel compared to a baseline flux of 0. On the right is the phase folded data showing the deeper transit model of planet C on top in blue and the shallower and longer transit model of planet B underneath in orange. Both of these planets have been modeled as Keplerian orbits in the exoplanet package. So we can now also look at our radial velocity data from the HARPS and PFS spectrographs. This data has been modeled with the same radial velocity GP in green, and I have chosen to cut out the times where there is a lack of data between observations for the sake of clarity in this presentation. In the top panels, we can see the HARPS RV data points as purple circles and the PFS data points as orange triangles, along with the GP model for the radial velocity in green, with its 1 and 2 standard deviations in lighter shades. Below this are the individual models for the planets, offset by 4 meters per second each for clarity, followed by the combined model of both planets in red and the RV data points lying over the top. And lastly, our residuals compared to an RV baseline of 0 meters per second. Similar to our test data, we can phase fold our radial velocity data from both observations, with the data points from each instrument labeled the same as before, and the model for planet B in orange on the top, and model for planet C in blue underneath. Using the HARPS data, the team at Porto University were able to derive some stellar parameters for us, including the likely mass of the star of 0.648 solar masses, a radius of 0.564 solar radii, an effective surface gravity log G of 4.743, an effective temperature of 4,552 Kelvin, and lastly, a metallicity of approximately minus 0.284. So we can therefore place the star as a K-type dwarf. Further to this, we also predicted a stellar rotation period of 21 days based on modeling of the HARPS data in the data platform. This was then supported considerably by WASS-SALS data provided by Cole Hellier, showing a clear peak around 21 days in the periodogram on the right, making this our most likely stellar rotation period. As a result of our modeling with the data sets presented, we have obtained various planet parameters, although it's worth noting that all of these values presented are the current best estimates, which will be further refined as more data sets are added to the global modeling and exoplanet. We find that the inner planet B has a mass of approximately 4.36 Earth masses, a radius of 1.42 Earth radii, and it sits on an orbital period of 3.82 days. So this places it comfortably in the regime of super-Earths. Likewise, planet C has a mass of approximately 9.53 Earth masses, a radius of 2.07 Earth radii, an orbital period of 8.59 days, placing it as a mini Neptune type planet. Further to this, we can plot where our current preliminary estimates of the masses and radii will place each planet on the mass radius diagram, which was plotted in Fancy Mass Radius Plot by Oscar Barragan against exoplanets from the TEPCAT catalogue, along with composition models from Zheng et al. 2016. From this, we can estimate that TOI 836b in orange is consistent with a planet with a composition of 50% iron, 50% MgSiO3, and planet C in blue lies somewhere between primarily MgSiO3 and 50% MgSiO3 and 50% water. Again, these values may change as our model improves, but this helps to contextualize our planet discoveries amongst the wider catalogue of confirmed exoplanets. Some of our upcoming work includes integrating the new data from Sector 38, which was released not long ago. And as we can see from the plot on the right-hand side from the Spock pipeline of tests, the star continues to be very active. So we will need to consider our GP modeling and the TTVs we have encountered in other observations when dealing with this data. We will also be integrating further photometry and RV data from our many sources and modeling the extent of the transit timing variations. Some possible future prospects for the TOI 836 system include atmospheric characterization of the planets from transmission spectroscopy, and KAOPS is an absolutely key element of this discovery if we wish to further constrain the orbit and properties of planet B, which, as I mentioned earlier, is particularly difficult to observe from the ground. Finally, I would like to thank my PhD supervisor, Dan Bayliss, for all his assistance and guidance thus far, Dave Armstrong for obtaining data from the HARPS spectrograph through the NCORS program, Johanna Teske for providing data from the PFS spectrograph, Tom Wilson and Hugh Osborne from the KAOPS team, Vardan, Sergio, Nuno and Elisa from the Porto University team for their stellar parameter analysis, Cole Hellier for analysis of the WASP South data, and finally, Aries Osborne and Ed Bryant from the University of Warwick for providing assistance and tutorials for the Exoplanet package. And of course, thank you very much to all of you for listening, and I'm happy to take any questions that you may have.
Thank you very much. Well within the time, so we should have time for quite a few. Sorry, Tom.
No worries at all. Yeah, I was just going to say what a fascinating system it is with 2 planets across the Radius Valley and this metal poor nature of the host star. So on that topic, we have a question on the Slack channel from Jake Clark. Great talk, Faith. I see that the star is iron poor. Did you model the alpha abundance at all? Would love to know whether or not it's a thin or thick disk star.
So this is something that we haven't yet looked at. I think it's quite interesting as well to note that as well. It is very metal poor. I'd be interested to know sort of how this might affect some of our planetary parameters too, but at the moment we haven't yet looked at this. We are still aiming to actually fold in all of our other radial velocity and transit data before we start looking more in depth at some of these external factors as well. So not quite there yet, but we will be one day.
Yeah, Hugh asks or says, Faith, awesome planets. I'll be interested to see what the TTVs reveal. And asked a question, did you use activity indicators to constrain the GP when fitting the RVs?
Yes, we do use activity indicators for each of our fitting, as for all of our fitting as well, particularly as the star itself is very active. We see this particularly in the sector 38 observations, but also somewhat in sector 11. So when we were dealing with our RVGP modeling as well, we were mindful of the stellar activity. Now, if I maybe just go back to it. Sometimes my slides don't move. Yeah, there we go. So yeah, we are continuing to be mindful of the stellar activity as we go forward. I'll also be interested to see kind of how the TTVs come out of this and what the true source of them perhaps is. My first sort of thoughts, maybe it could be something to do with the activity as well. We haven't yet detected any kind of third planet, although that could be another possible source we haven't found yet. But yeah, thank you very much for your question.
Brilliant. If that's all, thank you very much, Faith. I've also seen that TOI 836 will be observed by JWST in cycle 1. So I think it's fair to say that this won't be the last that we'll hear about this system.
That's definitely good news.
Brilliant.
Great, thank you very much.
All right, thanks everyone for providing an excellent program of science talks, and I'll hand over to Diane, who will be moderating the Lightning Poster talks, but you might see me again in a few minutes.
Hi everyone, so I'm Diana Dragomir. I'm one of the co-organizers of this winter session. I work on exoplanets and currently at the University of New Mexico as an assistant professor. So I don't want to take up too much time. I'm just, as I put in the Slack, I'm going to call people's names. You can introduce yourself and your project if you want. Hopefully you will. And just one final thing I did not mention in Slack, which is when you want the next slide, please say so, because Hugh will be sharing the slides and he will wait for your cue to move to the next slide. Okay, so without further ado, I'm going to start at 3 minutes now for Sasha Gershwa.
Thank you, Diana. My name is Sasha Shiva. I'm from the RIU Planetary Research at the University of Cologne, and we have a large history of detecting and characterizing exoplanets from space missions, starting with Corot in 2006. Next slide, please. But this time we usually use periodic algorithms which used for periodic transits, BLS-like things. But this time I come up with single trans. This is a new development to detect single transits. As we hit before with the dual transit talk, these single transits are very interesting. If you look at this left, you see a very rough calculation for detected planets per period for Kepler, K2, and TESS. It's calibrated to about 1,000 detections, was in December 2019. And as you can see, of course, there are a lot of transiting planets with larger periods missing in TESS and also in K2. Of course, it's obvious because of the baseline, but if you calculate the probability for single transits, you see directly, you can calculate easily that there are more than 400 single transits are undetected in TESS data. And of course, these are mainly transits of small planets or small candidates at first. And we developed a new algorithm for the detection using our wavelet-based techniques. We use an exotrans also, and a new detection method to detect the transits. And as you see here, this is a simple. We detect the transients of the ingress and egress using green and red. And as you saw in the example before, it's possible to detect, even in this example, yes, you detect a lot of transits, and there's a lot of help in using this green and red. Yes, okay, green and red. And of course, we do some in the next duration. We check them and the Amanda-Argot fit. And of course, the goal is it's an ongoing, which is an ongoing thing of detection of single transit of small planets, which is funded by the German DFG and the priority program. And we will also search all the archival data from the Corot, Kepler, K2, and TESS in this program. And of course, single transits found here can be observed with KEOPS for additional transits. Of course, maybe with some RV follow-up first and other detection. This is also good for single transit for revisits and tests or future missions like Plato. And this single trans works also very quick and is therefore also good for periodic and quasi-periodic transits for strong TTV and circumbinary planets. So look at the poster. It's in the poster hall 5, I think left front. And if you have questions or contact me. Thank you.
Thank you. I don't think we have time for questions right now, but Slack channel is open for that. So next up we have Matthew Hooton.
Great. Hello again. Hot early type stars tend to be fast rotators, which causes the equatorial regions to bulge with respect to their poles. And due to a phenomenon called gravity darkening, this leads to the poles being significantly brighter than the equatorial regions. If you add a transiting planet into the mixture with an orbit that is misaligned with respect to the stellar equatorial plane, this leads to the presence of significant asymmetry in the resulting transit light curves. The main benefits of transits such as these is that they encode information that standard light curves of slow rotating stars do not. And this includes the true three-dimensional spin orbit angle psi that is challenging to measure using other methods. The main downside of it is that many of the transit parameters are highly correlated, which makes an accurate measurement of psi very difficult. Could we go next slide? So one well-established way to accurately determine the spin orbit angle from the light curve is to place priors on parameters including the sky projected spin orbit angle lambda from Doppler tomography observations. The study I'm leading, which should become available on arXiv very soon, I propose a new method where I use the joint fitting of transits acquired at multiple wavelengths as another solution where Doppler tomography observations don't exist. On the left, we have transit light curves from the hot Jupiter Mascaro 1b acquired with both Spitzer and KEOPS. The green lines show models where each transit is fitted separately, and the purple show two transits fitted jointly with a single set of transit parameters, apart from limb darkening. On the panel in the middle, we can see that the KEOPS only fit corresponds to a transit path in relatively poor agreement with the result from the Doppler tomography. However, on the right-hand side, we can see that a Spitzer plus KEOPS fit, which is in relatively good agreement with Doppler tomography. Admittedly, this doesn't include any test data, but my poster does, so come see it, poster number 4.20. And in addition, future studies could use KEOPS to target systems where asymmetric test light curves already exist. I'm done.
Thank you. Okay, we have time for one question.
Okay, Hugh in the Slack channel asks, how valid is the assumption that gravity darkening is uniform with latitude/time?
Well, it's something that we expect to, well, this is a relatively, it depends how you parameterize the problem. Essentially, the way it's parameterized in the model I use is that it is wavelength independent. And it is simply a function of one parameter, which is called beta, which originally was supposed to be one value, but we've seen slight deviations away from that. So currently I'm having it fixed to a value which has been stored in one of the Claritel tables, which seems to provide relatively good fits. If I change it slightly, we get still good fits with marginally different parameters. So it's a problem which is quite difficult to fit for in this method, or indeed most other methods. But well,
I think the 3 minutes are up.
Look into it. Thank you.
Okay, up next we have Gaia Lachadelli.
Yeah, hello. So I'm Gaia Lachadelli, from a PhD student from the University of Padua, and today I will briefly present to you the work that we have done and we're currently doing on the TOI 561 system. So this system was firstly observed by TESS in Sector 8 in 2019, and there were identified 3 possible candidates. So we decided immediately to follow up the system with ARPS North, and from our good data set of 82 radial velocities, we could recover the 2 inner planetary periods, but actually not the 3rd one. And what we found was that there were 2 additional new signals at longer periods. And so at that point, we proposed a totally new configuration, assuming that the 2 transits of these 3rd TESS identified candidates were actually 2 single transits of the 2 additional longer period planets identified in the radial velocities. And there was a very good agreement between the ephemeris from the radial velocity only and the photometric fit only. And the system was also dynamically stable. And so the main point is that we were able to infer the mass and the radius of the 4 transiting planets in this system. That are namely an ultra-short period super Earth, which has a very, very low density, and 3 additional longer period mini Neptunes. And another interesting fact is that this star is a metal poor thick disk star, which is interesting in itself. Next slide, please. Okay, and here comes the second part of the story. So we also decided to follow up the system with a Cheops satellite, which was very suitable for our purpose, which was on one side to confirm the proposed planetary configuration using Cheops photometry, and on the other side to probe the internal structure of these planets using very precise radii, so with precision below 3% with Cheops, and also to improve the precision on the masses thanks to a second ARPS North radial velocity campaign. And so this is work in progress, and so stay tuned for the new results. And so thanks for listening, and thanks, really, I want to thank also all the collaborators and the ARPS North and Cheops team that are, of course, contributing to this work. And with this, I'm done.
Any questions? I see someone's typing. Quick question from me. Are you finding any signs of new, like a 5th planet or anything in the system?
Yeah. Okay, yeah. So we were still working on this, but it seems that it could be an additional longer period planet. This is in the new radial velocity because we already spent a very long baseline, almost 2 years. And so, yeah, that's very interesting. It's new work going on.
Okay, I don't think we have time for any more questions. Thank you, Gaia. So up next we have Fan Yang.
Hi, everyone. I'm good now, right? I can hear. Okay, so yeah, I'm Fan Yang, working with Run Arbitrary, and pleasure to briefly introduce our result here. That is discriminating between the conflict measurement of the exoplanet transit parameters through the joint survey of TESS and Cheops. So next slide, please. Thank you. So this is about the transit depth comparison. The source is Cal19AB. And the radius ratio of the source, sorry about that. Yeah, next one, please. Yeah, this one, yeah, thank you. So the radius ratio of Cal19AB in test band is 2 sigma smaller than the previous work in the different band. The radius ratio difference possibly indicates a haze-dominant model atmosphere. Haze-dominant atmosphere, as shown in the red panel in this slide. And we also highlight about the bias that the lambda-ducting parameters as well as the sampling rate introduce the precise multi-band measurement. So next, please, the last story of this. So this one is about the trend timing variation of WASP 161B. The test timing are offset obviously relative to the intermediates as well as the reproduced timing from the archival light curve in the same paper. The TTV is about 6 minutes, which is about 5.5 sigma, and could be modeled with a perfect quadratic function, yielding a constant period derivative. This quadratic function might be dominated by the a model that a tidal dissipation would be the best explanation for the available trend timing variation so far. So that's all. Thank you. Okay. I'm fine.
Okay.
I'm good. Yeah.
I have a question. So previous slide.
Yeah.
What with the shallower transit? Hugh, could you go back
yeah.
a slide? The shallower
yeah.
transit, that was from which instrument?
The KL19AB.
The one in yellow?
Yes, the test result is the one in the real region, and the black one, the black line is the result from the previous one. So this radius ratio difference is about 7.5 sigma, but some of them is dominated by the systematic. So if you look at the reproduced light timing result from our pipeline, you can see that this radius ratio is not that significant, but it's still 2 sigma. So yeah, that's the result so far.
Okay, thank you. So our final poster summary is from Tom Wilson. Go ahead.
Thank you, Dana. Yeah, my name is Thomas Wilson. I'm a research fellow at the University of St. Andrews. I'd like to talk to you today about TOI 1064, which is the focus of submitted and hopefully upcoming paper, where we got KOPS and a whole bunch of observations from other instruments to detect and characterize the system. On the upper left plot here, you can see the one KOPS visit, and you'll notice, similarly to some of the data shown by James and others earlier today, there is this systematic roll angle trend. So in order to get rid of that, we developed a new novel PSF PCA detrending method, as you can see on the second panel on that plot in the black line, to model this variation and successfully used on the KOPS data to remove it, as you can see in the third panel. Combining these data with tests, as seen on the bottom left, HARPS radial velocities, NGTS, LCO, and ACE-TEP data, we confirmed the system and characterized both sub-Neptunes. We found that both planets have about a 2.5, 2.6 Earth radii, but they seem to have a significantly different mass, as you can see at the mass radius diagram in the middle, with planet B being one of the smallest and therefore most dense massive sub-Neptunes that we've known, that we found so far. We did some internal structure modeling and some atmospheric escape modeling, as you can see over here on the top right, and we found that B likely has a tenuous atmosphere, as given in gray, with a large water reservoir and silica iron core, whereas planet C likely has an extended envelope, as given by this large gray area. What we can do from the precise photometry and RVs we have for planet B and a whole bunch of massive sub-Neptunes is that we can have a look at their bulk density versus the host line metallicity, as seen in the lower right here. And curiously, we have noticed a seemingly a trend between this density and stellar metallicity for massive sub-Neptunes, which may hint at planet formation effects. And yeah, that's my home.
Okay, I don't see any questions in Slack, so I'm gonna ask what the periods of these two planets are. I guess you said them, but
B is at roughly 6 days, and C is at roughly 12 days. Give or take.
And what's the star?
It is a K dwarf. Yeah, solar type K dwarf. Solar metallicity K dwarf. Yeah.
Okay, cool. Thanks. All right, so I think on that note, we are done with the poster summaries. Thank you all for keeping on time. And Hugh, do you want to say any final words?
Thanks, Diana, and thanks, Matthew and Thomas, for also organising this for me. So yeah, I'm sorry we're in a little bit over time, but there's so much K-Ops science to fit in that it can be difficult to get it into 2 hours. But yeah, thanks so much for attending. There is a Juno talk in the main room 1 in about 2 minutes time. So we just about managed to squeeze it in before that starts. So if you want to go over to room 1 to watch that, that's the conference continuing. But for, yeah, that's the end of K-Ops, but there is Willie's talk on Friday. So if you want to hear more about K-Ops, you can attend the future missions panel. But yeah, thanks very much, and bye.
Bye, everyone.